by observing some of the interesting features of the heat transport when there is a fluid which is flowing through a pipe. So, we are going to develop further on that. So, just to recap, so we said if it is a constant flux boundary condition, so note that without solving the equations in the fully developed regime, we said that dt by dx that is equal to dts by dx, that is equal to dtm by dx, and that is equal to constant. Okay. So, not just that, so Ts is the surface temperature, again this is in the fully developed regime, and Tm is the average or the mixing cup temperature. So, similarly we also showed that for constant temperature boundary conditions, we said that dt by dx is Ts minus T by Ts minus Tm into dTm by dx. So, obviously this is not a constant, you can clearly see that it is not a constant. Okay. So, we are going to develop further from here and see what we can gain from these useful insights, and also today we are going to actually solve the full model equation and then look at how these kinds of insights actually is going to help in solving the full model equation. Alright, so let us look at the constant temperature case. So, we said that dTm by dx, so we wrote an overall energy balance for the mixing cup temperature, and we found that that should be equal to Qs prime P by m dot Cp. So, note that the minus sign will depend upon the direction of the heat transport from the fluid to the surrounding or surrounding to the fluid. Okay. So, now if it is a constant temperature case, obviously the flux is not constant, Qs double prime is not constant. In the last lecture we showed what is the mixing cup temperature profile when the flux is constant or the constant flux case. So, this equation is an equation for every location in the pipe. So, this is a general balance which we wrote from x equal to 0 to x equal to L. Okay. So, this is valid for x equal to L. Okay. So, now, so the flux is not constant. However, from Newton's law of cooling, we know that flux is h into Ts minus Tm. Okay. So, that is by definition, right. So, now we can use this expression here equal to Ht by m dot Cp Ts minus Tm. Okay. So, now if we integrate this expression, we should be able to find the profile of the cup mixing temperature, right. So, we are going to do something slightly different. So, now I am going to define a variable called delta T. Okay. Okay, delta T is the temperature difference. So, delta T is Ts minus Tm. Okay. And so, now I can replace the whole expression in terms of d delta T, in terms of delta T. There is a specific reason why I call it delta T. In fact, you will see in a short while what is the rationale for that and how you can connect with some of the experiments that you have actually performed in the lab. Okay. So, now I can integrate this expression here, ln that is equal to minus Hp by m dot Cp. Okay. So, delta Ti is nothing but delta T at x equal to 0 and delta T naught is delta T at x equal to L. Okay. So, this is the delta Ti is nothing but Ts minus Tm at x equal to 0 and that will be Ts at x equal to L minus Tm at x equal to L. Okay. But we said it is a constant temperature condition. So, this is nothing but Ts minus Tm. Ts remains constant along the surface. So, it is Ts minus Tm at x equal to 0 and x equal to L. Okay. So, this is nothing but the temperature difference of the average fluid temperature and the surface temperature, and this is the temperature difference at the exit of the tube. So, these two are actually measurable quantities. I can now find out what is the average temperature at the inlet, I can find out what is the average temperature at the outlet of the tube, and these two are measurable quantities. And so, delta Ti, I stands for, I stands for input and O stands for output. So, these two are measurable quantities, experimentally measurable quantities. So, therefore, ln delta T naught by delta Ti, that is equal to, what is integral 0 to L h dx? Yeah, it is what? H bar into L, right? So, this is the, minus P into L into H bar defined based on the length of the circular tube. That is the average heat transport coefficient. Remember that we are really not very interested in the local heat transport coefficient. What is more interesting and important is the average heat transport coefficient, okay? And that is an important design parameter, okay? M dot C. Now, if I look at the total amount of heat that is lost by the fluid, okay. So, the net amount of heat that is actually lost by the fluid due to convection, okay. So, that is given by m dot Cp into the mixing cup temperature at the outlet minus the mixing cup temperature at the inlet. So, that is the net amount of heat that is lost by the fluid by simply looking at the difference in the capacity of the fluid at the inlet and at the outlet. So, now I can use this expression and substitute for m dot Cp. So, I will have ln delta T naught by delta Ti, that is equal to T into minus PL H bar L divided by Q convection into Tm x equal to 0 minus but we know that delta T naught and delta Ti are the difference in the surface temperature and the corresponding cup mixing temperature, right. So, I can rewrite this as minus PL H bar L Q convection. So, I can add and subtract a surface temperature term here. So, I will get Ts minus Tm x equal to L minus Ts minus Tm x equal to 0. So, all I have done is I have just added and subtracted Ts, and so this is nothing but this is delta To, right, this is the output. So, this is the minus P L H bar L by m dot Cp Q convection into delta To minus delta Ti. So, this is the temperature difference at the outlet, this is the temperature difference at the inlet. Okay. So, from here I can rewrite, estimate what is the net amount of heat that is transferred. So, that is given by H bar L P into L delta Ti minus delta To divided by ln delta Ti by delta To. Okay. What is this expression? This is the log mean temperature difference. Okay. So Q convection, what is P into L? It's the curved surface area, right? So it's H bar L into the curved surface area into delta T LMTD. So it's not just a magic that you use log mean temperature difference in your calculations. It's actually rigorous analysis that shows that that is the correct temperature difference that you should actually use for your heat transport calculations. So log mean temperature difference is what most of you who have done this laminar and turbulent flow experiments, you would have already encountered this term called delta T LMTD, and in fact that comes from a rigorous analysis of the tube experiment, heat transfer from a fluid which is flowing through a tube, and in fact one could show similar exercise for the fluid which is flowing outside the tube as well. Okay. So delta T LMTD is actually the correct temperature difference for heat transfer calculations. So what we learn from here is that the log mean temperature difference is the correct temperature difference that you have to use for heat transport calculations, not always when you are using the measurable properties. The reason why this is the correct measure is that you cannot measure the local temperature profile. So only measurable properties you know is the input and the outlet, inlet and the outlet temperatures. So if you know the inlet and outlet temperatures, then delta T log mean temperature is the correct temperature difference that you have to use for finding the total amount of heat that is transported. Yeah. This expression is valid for both. So I'll show you in a short while. Actually, when you have, let's say if you have a fluid which is flowing outside the tube, okay, which is at a certain temperature, okay. So this can actually be extended to varying temperatures also. We used a constant temperature, but you can also use the same expression, same delta T log mean temperature for the varying expression, which have varying temperature, which we will see when we are actually going to do the heat transfer equipment design. There we will see that this is a general expression which is valid for whether you have constant or a varying temperature. So we'll see that when we actually look at the heat transport equipment design. So suppose we say that there is a fluid which is flowing. Okay. So there is a fluid which is flowing through the tube, and there is another fluid which is flowing around the curved surface, and let's say that this is at a temperature T infinity. Okay. So now one could define the local flux of heat transport, okay, can be defined as H into T infinity minus Tm. Okay. So what we know is only the temperature of the fluid which is flowing past this tube, and so we define the net flux of heat transport at any location as heat transport coefficient multiplied by the temperature difference of the fluid which is outside and the mixing cup temperature at any cross section. Okay. So that's a definition by the way. So now if I incorporate that definition here, so I'll have Q convection will be equal to some heat transport coefficient. I write this as U, and I'll explain in a short while why I use U here. U into AS into delta T LMTG, where delta T I is defined as minus So, the U is what is called as a universal heat transport coefficient. Okay. So, U is the universal heat transport coefficient. The reason why it is universal is the wall of the tube is a certain definite thickness, right. So, there is going to be resistance to conduction in the wall of the circular tube, and there will also be resistance for heat transport between the external surface and the fluid which is actually flowing past it. Okay. So, universal heat transport coefficient, essentially it accounts for what is the heat transport coefficient for transport from the fluid to the wall. So, if I zoom this location, so if this is the wall of the tube, so there is fluid 1 which is flowing here and fluid 2 which is flowing here. So, you could have a heat transport coefficient at the internal location for heat transport from fluid 1 to the wall of the circular tube, and then there will be heat transport from the inner wall to the outer wall of the tube, and there will be heat transport coefficient for transport of heat from energy from the wall to the outside fluid. So, this U, universal heat transport coefficient, it essentially accounts for all three quantities. Okay. We will see a lot more of these when we are actually looking at the design of heat exchangers. We will see what is the definition of universal heat transport coefficient. We have seen very briefly when we discuss conduction, but we will see in a lot more detail as to what is this universal heat transport coefficient, what are the different factors that are accounted in that universal heat transport coefficient. So, this is what this U is what most of you would have used if you did your laminar flow and turbulent flow experiments. It's the universal heat transport coefficient concept is what you would have used to estimate the heat transport coefficient for that experiment. Okay. So, we will see a lot more details about what are the different factors accounted for, what are the different quantities, and what are the different pieces of the universal heat transport coefficient that you can neglect under different conditions. Okay. So, that we will see, we will reserve it till the heat transport equipment design. Alright. So, all the things that we have studied about heat transport through internal flows is so far only about the characteristics and properties of the heat transport coefficient. We never found what is the actual number, right. So, that is what we are interested in.